Hi everyone. Today let's talk about sessions 11.3, dot products. Let V and W be vectors. Let theta be the angle between V and W. The geometric descriptions of the dot products is V dot W equals the length of V times the length of W times cosine of the theta between them. So note that dot product of the two vectors is a scalar, not a vector. Okay? A lot of students actually make these mistakes. The dot product is a scalar, it's a number, not a vector. Okay, so we get the following descriptions of magnitudes of a vector in terms of dot products. So V dot V equals the length of V, okay, square. Another way to write the length is defined to be the square root of V dot V. And actually, this is the general definition of the magnitude of a vector in a vector space. Okay, so for example, R3 is just one example of the vector space. There could be other vector space, and in general, we can use the dot products, and we can use dot products to define the length of the vector. Okay, and we do have some physical intuition for dot products. If F is a force vector that is applied to move an object along a displacement vector D, okay, so this is the force, and this is the displacement. Then F dot D represents the work done on the objects. Okay, so let me draw some picture here. So theta is the angle between F and D. Well, please consider this. Okay, so I write down this line segment, and then I form a right angle triangle. And you know, this guy, the magnitude of F is right here. Then what is the length of this guy? Well, if we call it X, well then X is the adjacent, right? Then the length of F is the hypotenuse. Well, then you get the X over adjacent over hypotenuse is cosine theta, right? So X is the magnitude of F times cosine theta. So what does that mean? Well, that is like the projection of the force. Okay, so it measures how much force actually acting in the direction of the displacement. Okay, so that's why we can. So this is the force portions that is adding in the directions in the displacements. Then we can use it to multiply by the displacement. That will give us the work done. Okay. Next, the dot product satisfies the following algebraic rules. For vectors u, v, w, and scalar r, we have u times v equals v times w. Okay, so this is the commutative law. So dot product is commutative. And then next, we have the scalar multiple. Okay, you can multiply the r by the v, or outside the uv, or remember u dot v just give us a number. Okay, so we can use a scalar times a number, or you can multiply the second vector by r, so it's the same. Okay, so this is scalar multiplication. Next, u dot parentheses v plus w equals u dot v plus u dot w, or u plus v dot w is u dot w plus v dot w. So this is the distributive law. Okay. Next, let's see what happens when we compute the dot products of the standard basis vectors. Okay, we call what are the standard basis vector? I is 1, 0, 0. J is 0, 1, 0. K is 0, 0, 1. right? And they are all unit vectors, which means the magnitude of all of them are 1. Okay, so we keep in mind now u dot v is the magnitude of u times the magnitude of v times cosine theta. Theta is the angle between them, okay? So because now all of the magnitudes of the ijk are 1, so when we dot the products, well, if this guy is 1, this guy is 1, then the dot product is just gonna be cosine of the angle between them. Okay, but do you remember those letters in R3? So this is I, this is J, this is K. They are in the X direction, Y direction, and Z direction respectively. What are the angle between them? Okay, the angle between them, all of them are pi over 2, which is 90 degrees, right, everybody? So that's why cosine pi over 2 is, anyone know the answer? 0. Okay, so that's why I and I, then the angle between them is 0. Cosine 0 is 1. Okay, so that's why we have 1 here. But J and I, because the angle between them is pi over 2, so that's why the dot product is 0. Okay, I and J dot product is 0. J, the angle between them is 0, so cosine 0 is 1. And K and J, the angle between them is pi over 2, so 0. Here, 0, 0. Here, KK, the angle between them is 0. So far, so good, everybody? Okay, so this gives us the components formula. Okay, so use the table above, and together with some algebraic rules, we can obtain the following simple formula for the dot products. So if we have the components v1, v2, v3, and w, we have the coordinates w1, w2, w3, then the dot product is given by v1 times w1 plus v2 times w2 plus v3 times w3. So we multiply each component respectively, and then we add the results. So far, so good, everybody? Alright, let's look at some example. So find v dot w for the given pair of vectors. Okay, so let's look at the first one. V dot w is minus 2 times the first coordinate of w is negative 3. Then we have 3 times 7 plus 4 times minus 5. Okay, negative 2 times negative 3, we have 6. 3 times 7 is 21. 4 times 5, 20. So we have minus 20. 21 minus 20 is 1. 1 plus 6 is 7. So I strongly recommend you, if you try not to use your calculator in your homework, after you're done, you can use your calculator to check your answers. But some calculation like this, try not to use your calculator, okay? We can practice our calculating skills. Okay, next, v dot w. Well, that's 1 times 2. And then we have minus 4 times minus 4 with minus 3 times 6. So this is 2. Minus minus become positive 16. 3 times 6 is 18. So we get 0. What can you say about them? We can say v and w, they are actually orthogonal. Okay. So two non-zero vectors v and w are called perpendicular or orthogonal if the angle between them is pi over 2. In this case, we write v is orthogonal to w. Okay, so this is the plus, but this perpendicular is you don't You don't go, your vertical line won't go across the horizontal line. Okay. And here we have relation between perpendicularity and the dot products. Two non-zero vectors v and w are perpendicular if and only if v dot w equals, any guess? 0. What is that? Because remember, dot product is v times w times cosine the angle between them. Because these guys are not zero, they're non-zero vectors. Well, then the dot product equals 0 if and only if the cosine theta is 0. Well, that's the same as the angle between them is 90 degrees. So far, so good, everybody. If we restrict the angle is between 0 and pi, okay, then the angle between them must be 90 degrees or pi over 2. Okay, so this is a very convenient formula for us to decide whether two vectors are orthogonal. Let's just calculate their dot product. Okay, so v and w, so v dot w equals 2 times minus 4 plus 6 times 1 plus 1 times 2. Well, that's negative 8, 6, and 2. Ooh, the result is 0. So are they orthogonal? Yes, they are orthogonal. So far, so good, everybody? Alright, let's look at more examples. Okay, so here, let's look at this example. Okay, let v be 4, minus 3, and 2. How many unit vectors are orthogonal to v? Okay. Let's draw some pictures. In R2, okay, in R2, two-dimensional space, xy plane. If this is the vector v, how many unit vectors are orthogonal to v? Well, orthogonal, it means it must pass through. It must on this line, right? So it is orthogonal. How many unit vectors are there? Well, this one. Right, so the length is 1. There is another one here. The length is also 1. So there are 2 unit vectors that are orthogonal to v in R2. So far, so good, everybody. Okay, how about R3? How many unit vectors are there orthogonal to v? Well, we have v here, but we can actually have a plane that is orthogonal to v. Okay, so this vector is perpendicular, is normal to the plane. Okay, then every vector on this plane is orthogonal to v. If we just consider the unit vectors, well, it will give us what? It will give us a circle. Okay, this is a circle with the radius 1. Okay, so how many unit vectors are there on a circle? Still infinitely many. So far, so good, everybody? Okay, so the answer in this case is infinitely many unit vectors are orthogonal to v. Okay, B, we want to find all unit vectors that are both perpendicular to v and parallel to the xy plane. Okay, what does that mean? Let's say this is v, right? And we want we know on this circle, we have the unit vectors that are perpendicular to V, and furthermore, we want to find the unit vectors that are also parallel to xy plane. You know, this is xy plane, right? Parallel to xy plane, what does that mean? So parallel to xy plane means the z coordinates is 0. Right? If you're on the xy plane, you don't have a z coordinate, right? So what are we looking for? Let me draw it. So you want to parallel to this xy plane. So it could be this one, it could be this one. Okay, then you let me see. It should be. Let me. So okay. Let me draw it better. Okay, so it could be this one, it could be that one. Okay, so there should be two vectors that are orthogonal to V and also parallel to the xy plane. Okay, so let's write down what we said. So let U be the unit vector. Okay, then because the z coordinate is 0, then we can set it up as x, y, comma 0. So far so good. Okay, because the z coordinates is 0. Okay. Then because u dot v is 0, then we get 4. So 4 times x minus 3 times y plus 2 times 0 equals 0. So this is what it will give us. The dot product with the v is 0. Next, it is also a unit vector. What does that mean by saying it's a unit vector? Okay, the magnitude of u is 1. So it means square root of x squared plus y squared equals 1. Okay, but it's the same as saying x squared plus y squared equals 1. This is easier because, well, if we want to include square root in our calculations, it's kind of hard. Okay, now we have a system of 2 equations, but one of them is not linear. Okay, in this case, we should use substitution method. Okay, so if we have system of linear equations, we use elimination method. But if we don't have linear equations, it's better to use substitution method. Substitution method, which means you want to solve for x or you want to solve for y in terms of x, and then you plug into the other equation and then you can continue to solve for it. Okay, in this case, let's see. Let's solve for x. Okay, so from equation 1, we can move the 3y on the other side and then divide it by 4. Okay, we solve for x. Then we can plug in equation 2. So plug in equation 2, we get 3. So 3y over 4 squared. That is 3 squared, 9. Y squared, 4 squared is 16. Plus y squared equals 1. Well, this is the same as saying the common denominator is 16, and then 9 plus 16 is 25. So y squared is 16 over 25. Then y equals plus or minus. When you take square roots, don't forget plus or minus. Okay, 4 over 5. Okay, and how about the x? Well, x is 3 over 4 times, it could be plus or minus 4 over 5. You see, 4 cancel, so that's why we get plus or minus 3 over 5. What does that mean? If x is the positive 3 over 5, and then the y is the positive 4 over 5. Okay? Or if x is the negative 3 over 5, then the y is the negative 4 over 5, 0. So far, so good, everybody? Okay, so here be careful if you multiply the number by negative number, so plus or minus, and when you multiply by negative number, it becomes minus plus. So be careful of that. But just in this case, we have the x coordinate and y coordinate, they're either both positive or both negative. Okay, so those are the two unit vectors. They are both perpendicular to V and parallel to the xy plane. Okay, let's continue. Using the geometric description of the dot product, which is v dot w equals the length of v times the length of w times cosine theta. Theta is the angle between them. Then we know because cosine theta is between -1 and 1, right? So that's why when we multiply by length of v and length of w, we get this inequality. So when is this guy maximum? So maximum is this guy, which is when cosine is 1. When is cosine is 1? Imagine here the angle between them is either 0 to pi, okay? So it's maximum when the angle is 0, okay? So we say V and W point in, any guess? The same direction. Okay, and when does it minimum? Minimum is this guy. When cosine theta equals -1. When is it cosine theta is -1? Well, that's when theta equals pi. What does that mean? That means they point in the opposite direction. Okay, so picture, we have the V here, we have the W here. And here we have the V and we have the W. Okay, and theta is acute. So acute means cosine of theta is positive, right? So the dot product will be positive. Theta is obtuse when the dot product is negative, because cosine of the obtuse angle is negative. Why? Look at the picture of cosine. Cosine looks like this, right? This is 0, and this is pi over 2, and this is pi. So for an acute angle, cosine is positive. For an obtuse angle, cosine is negative. So far, so good, everybody. All right, let's continue. Determine if the angle between V and each of the given vectors below is acute, obtuse, or pi over 2. Okay, so let's do it. V dot A equals 4 times 1 minus 3 times 2 plus 2 times 1. 4 times 1 is 4, 3 times 2, 6, 2 times 1, 2. Oh, it equals 0. So what's the angle between them? They are orthogonal, so the angle is pi over 2. Alright, so please pause the video and try to do the rest. And then after you're done, we can continue to check our answer, okay? Are you done? So we have 4 times 6 minus 3 times 8 and 2 times -1. 4 times 6 is 24. 3 times 8 is 24. And then -2. Oh, it's -2. It's negative. What do you say? The theta is obtuse. Okay, V dot C equals 4 times 5, -3 times 6, 2 times 3, 4 times 5 is 20, then this is 16, that is 6, so that's 2 plus 6, which is 8. 8 is positive. What do you say about the angle? The angle is acute. Okay, so we can use dot products, and then we can know like what's the angle between them. Okay, so far so good. Yeah, in general, we can actually know the angle between them. So here we know it's acute up to the power 2, but in general, we can solve the cosine theta is u dot v over magnitude of u, magnitude of v. Okay, and then we can do add cosine to find the angle. Okay, so the angle is add cosine of this number u dot v and magnitude of u, magnitude of v. So far so good, everybody? Okay, now let's continue in video part B. See you soon!